Well, thanks so much. Thank you, everyone, for being here. Good morning. It's my pleasure to be here today to present our paper on diagnostic load testing and refined analysis of concrete box culverts. Before I get started, I'd just like to acknowledge my fellow colleagues and co-authors on the paper. Christopher Gens, who was in charge of all the instrumentation and field testing. Andy Foden, who was our Bridge Technology and Evaluation Manager. He was the technical lead on this project. And Binyam Argawi, who was the project manager from the Texas DOT. So with that, here's the agenda for the presentation. We're going to dive into some methodology, background, history behind this project. Then we're going to go through the details of the load testing and computational modeling to get us to the refined load ratings of these type of structures. So this project was done with Texas DOT. They have about 19,000 of what they call bridge class culverts in their inventory. And based on their definition, bridge class culverts are basically bridge structures that can carry live traffic, and they have an opening of greater than 20 feet. They are part of MBIS, so they receive routine inspection. And historically, Texas used assigned load rating for these type of structures. And based on the definition, we can use assigned load ratings. If the plans are available, we know the design load of those. There's no need for a specific type of load rating based on what we saw in the inspections. And none of the principal structural members have a condition rating of below 5. So they're all in the moderate to good conditions. However, FHWA published this memorandum in 2017, asking all the owners and DOTs to only use assigned load rating for structures that are either designed or checked by the LRFT or LFT code, meaning that the design loads needs to be either HS20 or HL93. Well, Texas used a level of stress up until late 1990s. So for majority of these culverts that they had in the inventory, the design was based on ASD. So in a mutual collaboration with FHWA, Texas actually took the lead on refining some of these ratings. So they picked a group of that population, about 1,600 of these bridges, and they performed a load rating analysis using their in-house software called CulvLR. And the result came out that showed that the need for the posting on some of these culverts, some of them are on interstate system, they have been in service with unrestricted traffic for many years, some of them 50, 60 years. There was no sign of distress or deterioration in these culverts, and the analysis for some of them actually showed that these culverts are failing under their self-weight, under their load, which it's not very true because we saw them standing tall out in the field. So we suspected that there's some level of conservatism involved in the analysis and the load rating, and that can be rooted down to the assumptions with respect to the live load distribution in the culverts. It's usually based on the equations in the AASHTO, and the main contributor to those equations are the fill height. So this was the main story and the meat behind this project. So if we propose this methodology to perform a multi-step process to refine the ratings of a smaller group of culverts, about 44 to be exact, through a combination of diagnostic load testing and refined analysis. So the 40 plus culverts are assigned to us. We selected 10 of them for our diagnostic load testing, and the goal here was to have a better understanding of their actual in-service performance and the load distribution between different elements. So for our selection criteria, we take a look at the different attributes. We wanted to include other attributes that we believe it would have impact on the load distribution, not only the fill height, but also like geometry of the culvert itself, the location of the culvert throughout different districts to capture the variation in the soil and the soil structure interaction, and also look at the design standard and the plans. We looked at the previous rating results to make sure that we fully understand the failure modes, the failure mechanism, the controlling sections. And finally, most of the culverts that we selected for testing, they needed load posting based on the previous round of load rating analysis. For the diagnostic load testing, as far as the instrumentation, we used a combination of the strain and deflection sensors. For strain gauges, we use gauge extension to kind of capture that non-homogeneous composite of concrete, make sure that you're not capturing the effects of micro cracks or sacrificial aggregates in our results, and we took care of that in our post-processing. As far as the instrumentation details, we kind of used a similar instrumentation plan for all these 10 culverts. So we instrumented one exterior cell and one interior cell. And we had that idea of having two sections instrumented. Section A, which is basically heavily instrumented and was intended to capture the direct response out of the live load. Section B was instrumented a bit lighter. It was spaced 6 feet from the section A and was meant to capture that live distribution along the length of the culvert. As far as the testing configurations, we used triaxle dump trucks provided by TxDOT to us. They were all weighted and measured before each test. We had 5 different loading configuration. Basically, we started with putting up the truck on lining up the real axles to the sections, and then we start pushing the truck to one side to capture that lateral distribution behavior. And then we had a test 5 configuration that had 2 trucks side by side. All of these tests were done at the crawling speed, so no dynamic testing, and we repeated each test 3 times for each culvert to make sure that we are able to reproduce the data and we get the robust test data. These are representative test results. On the left side, you can see the time history of deflection for the top of slab, interior, exterior cell, and 2 sections, section A and B. On the right, this is a snapshot. This is the maximum strain picked up at obviously the section A, which was heavily instrumented on one of the load cases for one typical culvert that we had. The next step was the analysis that we done, the refine analysis, and we did it in 2 phases, the 2D modeling and the 3D modeling. The goal of the 2D modeling was ultimately to do the refine analysis for load rating, and the 3D modeling was to do the calibration on these culverts. So I'm going to start with the 2D modeling. So modeling the culverts in the 2D fashion, basically that 1 foot strip is a common practice for load rating. What we did in this case, we included the soil structure interaction using plate elements in there. Before we started doing the heavy analysis on this project, we did a mesh sensitivity analysis to identify how much of the soil we need to include, because we know we were dealing with a lot of analysis and a lot of computation in this project. With the time crunch that we had, we wanted to make sure that we are computationally efficient and not sacrificing the accuracy at the same time. One other thing that we included in the model, as you can see, we included the effect of pavement. That is something that is not really captured in the code equations, but we believe based on what we did in the field with those 10 culverts, all of them had some sort of pavement, different thicknesses. So we believe that that would have impact on the load distribution behavior. And here's some representative graphics on showing the deflection under dead load and live load for these culverts. The next phase was the 3D modeling, which basically we did it first. We basically took the 2D models, we extruded them, and we created these 3D models to have the full 3D representation of the structure and use these models for calibration of the test results. Obviously, we had to go 1 level up in the as far as the element order and complexity. So now we have plate elements for the culverts and pavement and 8-node solid elements for the soil. We adopted the mesh and the limit of the soil that we got from our optimization and mesh sensitivity in the 2D models. And then we used these models, and loaded them with the same truck that we had for the testing as far as the measurement and the weights to do the calibration. So for calibration purposes, again, we loaded them with the same trucks. We captured the responses at almost the same locations that we had sensors and deflection and the strains, and we started our calibration process. So for the first round, the attributes in the models as far as the material properties were basically based on the plans or what we had in the previous rating. And obviously for the first round, we had a difference between what we had in the model and the test. Then we started an optimization process. We start making changes in the boundary conditions, the material element connectivities, the material properties within the accepted range based on our judgment. And this graph down below shows the progress through the model calibration. All the red lines are the models and the iterations that we made to get closer to the blue line, which shows the result from the test. We could have used the 3D models at this point to do the load rating, but that's not the common practice. That's number 1. Number 2, it was very challenging to create these models and to doing the post-processing. And number 3, we only had the test result for 10 culverts. We wanted to kind of leverage the knowledge that we gained from the test and apply it through the rest of the 30. And we wanted to use it throughout 2D models. But the main challenge was, again, that was the core of this project. How to go from the 3D to 2D, how to define that effective live load portion that goes into that 1 foot drip. And, well, the obvious answer is to use the ASCC equations. But we know that using those ASCC equations in this case caused the extra conservatism in the analysis. So we came up with the concept of 2D calibration factors. So what we did, we basically loaded the 2D models of these tested culverts with the full truck. and we capture deformation. Obviously, the deformation is going to be much higher because it's only a 1 foot strip that's taking the whole load. Then we get the ratio between the test results and the culvert and the 2D model results, and we plotted them versus the fill height as a parameter, and we came up with that equation, the purple line, that kind of covers the upper bound of the behavior for all of this, and that shows the 2D calibration. So if we apply that calibration to our 2D models with the full load, we're basically getting the same response as we get from our 3D tests or from 3D models or from the test. One other thing that I want to mention here, the equation and the graphics are shown based on the fill height, just as a parameter, which is believed in the industry to have a major impact. But the other attributes that we believe are important, such as properties of the material of the concrete, the geometry, the soil effects, they're all in there. They're hidden, they're inherent to the test data that we had. We took this little further step to make sure that we are not losing any aspects of three-dimensional behavior while we are going from 3D model to 2D model. So we did what it called the 2D, 3D correlation study. We picked 3 culverts out of the 10 that we tested. One without a fill, one with 2 feet fill, one with 7 foot fill. And we plotted the deflections from the test, from the calibrated 3D model, and from the 2D model with calibrated properties and the applied calibration factor. And you can see across the board, these deflection values are very small, and they're generally in good agreement. One trend that we observe, as you see, going from the no fill to 7 foot fill, the difference between the test results from the test and the 2D model, which is the first and the last column, start diverge from each other. And this is kind of intuitive and aligned with what AASHTO MB says, because as the fill height gets deeper, your culvert is going to sense less and less of the live load, and basically the behavior is going to be controlled by the dead load and the self-weight of the structure. So with that, we proceed with the doing the analysis, the refined load rating analysis of the entire population of the culverts that assigned to us. So all of the 2D models were created. We did the capacity calculation based on the plans, following the AASHTO MBE, using the LFR method. Obviously, the model is just giving you the raw data. You need to do the post-processing, apply all the applicable load factors, impact factor, multiple presence factor, which I believe in the standard spec we call it load intensity factor, and the 2D calibration factor that we came up with. There was one other step that we did for this project, and that was the introduction of the multi-step linear elastic analysis to kind of capture or model the progressive hinging. So in the previous round of rating that was done by Texas, there was a blanket assumption of reducing the moment of inertia for concrete to capture the cracking and placing hinges at the specific locations. It was a blanket assumption. It could be true for some culverts, but it cannot be true for all of them. So that could be a result, again, for unrealistic data and the result out of the load rating. So in this case, we proposed this method to kind of capture that in a stage fashion. So the first step or stage, we just assume everything is rigid, all the connections are rigid. And then we look at the plans and we see if we have rebars or we have enough development for those rebars to kind of support the capacity that we are calculating. If there's no rebars or there's no enough development, especially with the culverts that are like 60, 70, 80 years old, we put a plastic hinge in there to redistribute the loads. Then we perform the analysis. If the operating rating was less than 1, that means that particular section is being overloaded in flexure. But that doesn't mean the structure is failing. That means that that section is no longer capable of carrying that load. And then we start placing plastic hinges in a controlled fashion in those locations to redistribute the load for the remaining part of the structure. We did this in a very controlled fashion, meaning that we never placed a hinge in the middle of the slab or middle of the wall that causes any instability. We also watched the state of stresses in the soil around it to avoid causing any type of tension or fictitious anchoring mechanism that is not really there. So that's the really important part of this. And these stages were intended to simulate the progression of the load distribution through placing of these hinges. And the key part is we did not apply all of these 3 stages to all culvert. It wasn't a blanket assumption. It was done as needed based on the plans and based on the result of the analysis that we saw. So with that, this is the representative data results for the design vehicle HS20 for the 10 tested culverts. So you can see across the board with this approach, using the calibrated attribute, using the 2D calibration factor, and using the multi-step linear elastic analysis and progressive hinging, we were able to increase the load rating of these across the board. The same result happened for the rest of the culverts, not only for the design vehicle, but also for the legal and emergency vehicles. And when it comes to legal and emergency, it's very likely that these culverts over the past 40, 50 years, they've experienced some sort of the same level of loading. So now our results that we get out of the refined rating with being above 1 for operating lines better with the actual performance that we saw from them out in the field. So with that, this is just the summary and conclusion. The project focused on the refined rating of a specific class of culverts that were designed based on ASD method. They were in service for many years without any restriction on traffic, no sign of distress. But recent rating based on the modern code require load posting on them. And we basically proposed this multi-step process that includes load testing and refine analysis to gain that better understanding of load distribution in these type of structures, and essentially we help the owner to avoid posting on these type of bridges. Thank you very much.